Hello, and welcome to another one of Ethan's engineering videos. Today's video, I believe part 1, 2, 3, 4, 5. Yes, part 5. Technically part 2, component B, but I'm just going to number them 1 through 7, so I don't want to bother with any of that. Today's going to be a really quick continuation of the previous video. In the last video, we figured out how to use the secant method and the Newton's method to figure out the root of a function. And so today we're going to be taking the Newton method and we're going to be adapting it to use, to be used for any function with an arbitrary number of functions within it. So what that means is that we're going to take a vector of a bunch of different starting points and a function which takes a vector of points and outputs a vector of points. So it's going to be a real matrix-focused thing, and we're going to have to make some changes to how this thing works. We're going to adapt it to be able to handle matrices. But before that, we're going to have to define a new function. So I'm going to define something called func2. And I don't know why it's saying there's a bunch of functions that exist already, because I just restarted the runtime just to make sure everything was clean. Strange. Anyway, this is going to take a vector. I'm just going to call it vec. And it's going to return a jnp dot array. This, stuff like that. That's not what I wanted to do either. I wanted to start typing. So the first thing I'm going to do is I'm probably going to copy our function from way up here that we used before, because I like it. And then we're going to make up a couple other ones on the spot. So what else do we want? What if we did 2.1 divided by sqr, jnp.sqrt of, I don't know, jnp.abs of y. We're going to change this to a y, and this one to a y. Actually, this one's going to be a z. And then we're going to do plus jnp.sine of z plus 2x minus 4. These are going to be our two functions right here. Bracket is not closed. It's closed right here. Oh. So then what are x, y, and z? Well, we're going to unpack x, comma, y, comma, z from our vector. You could also do it by vector, like indice 0, vector indice 1, indice 2. But I don't feel like doing that. So this is just easier for me to kind of visualize it. This is going to be our new function. So this is going to be our two functions. Again, we could arbitrarily put a comma here and then do another one, which is just going to be x times y times z minus divided by x times y times z squared. Sure, so now we have three functions. And this is always going to be minus 10. My touchpad's still on. I'm going to turn that off really quickly. There we go. There we go. So those are going to be our three functions now, because I felt like doing it. So now, again, I came up with this function on the spot, so I have no idea what the roots are, but I do know the roots of this first one. So we're going to take our Newton, our old function, and we're going to rename it mtrx for Newton matrix. So what are the differences going to be between our old one and our new one? Well, the first thing I'm going to do is get rid of these notes, because we don't actually really need them. And the first thing, that's the first thing I'm going to do. I almost said the first thing I'm going to do directly after saying the first thing I'm going to do and doing it. So what change do we need to make? Well, now our function That's pretty much the same. It's still this thing. But this guy is expected to be an array of starting values. So we're going to need a vector that contains an x and a y and a z value. So that means x0 has to be a vector. So the first thing I'm going to do is I'm going to say x0 is equal to jnp dot at least 1d, because I want to make sure that whatever I put in, I just want, this is just for me safety proofing, so that if I type it in as an array of 3 numbers, it knows it's supposed to be a numpy array. That's just my personal preference. So then f0 is going to be the output of whatever we put x0 in. So we put in 3 vectors, we're going to get out a vector with 3, whatchamacallit's in it, 3, not scalars, I almost said scalars, 3 floats. So we're putting in 3 floats, we're getting out 3 floats. But then here we have the prime, the derivative. And that doesn't work because we now have 3 independent variables and 3 functions being outputted. So the gradient won't do what we need it to anymore. So we're going to upgrade our gradient into a multiple variable gradient, otherwise known as a Jacobian. And we're going to, instead of calling it f prime, we're going to call it f Jacob. So now we can no longer use that, so I'll just switch that out right there. So that's just kind of stays consistent. So that's, these 3 have been now adapted. So now what about our, for IM range? The first thing we notice is that right here we have this function, but again we have to remember that f0 is an array, x0 is an array, and f Jacob is now a matrix. So the first rule is you can't do division by a matrix. And I'm going to just scoot this x over so it's a bit more clear. x0 minus, I should probably change that in the old one, but I don't feel like it. So anyway, x0 minus f0 divided by f Jacob. And so the problem is you can't do division with matrices and arrays. Like, that's just not something you can do. So how do we take care of it then? Well, we have to do matrix multiplication, but instead of using the original, we have to do the inverse. So what we're going to do is we're going to get rid of the u here and do at, because at is the sign for matrix multiplication, and then f0. So now we're matrix multiplying them, but we're multiplying f0 by f Jacob at x0. But unfortunately, we need it to be division, so right now it's multiplication. So we're going to wrap this in parentheses, and we're going to use jnp.linalg.inverse. So we're going to take the inverse of the Jacobian, which is the same as, so then when we matrix multiply f0 by the inverse, it's like dividing by f of Jacob. That's taken care of. We then get our x1 out of that. Our x1, we plug that in to get our f1, and we check f1 for the tolerance of the absolute values. You might think we're done. However, we have to remember that f1 is no longer a single float. So less than our tolerance isn't good enough now. We have to consider that it's going to be an array. So do we just take the sum of it and take the absolute value? Like, how do we kind of accord that? And so what we want to do is we want to look at the dimensionality of all, the magnitudes of all of our things. So like, we could take the sum of that to be 0, but then if, that would be kind of unclean. We could square them, but then there's a bunch of ways we could go about doing it. But the best way is just to wrap it, instead of using the absolute value, I don't know why I just, so instead of using the absolute value, what we can do is do jnp.linalg, so, because again, we're working with a matrix, dot norm. So what this is going to do is it's going to, well, I can just, it'll tell you if I hover over it. Right here. So it returns, tell me what you're going to return. There you go. The norm. So what that's going to tell us is the magnitude of our matrix in all of its different directions, and to make sure that that is less than our tolerance. So that right there is pretty easy. That also is going to make sure that it's going to be positive. So this is like an absolute value, but extended across a matrix. And that's pretty much all the major changes we need. So all we have to do now is run Newton matrix. So as I said, we're going to use our function 2, which I think I literally just called func2. Just double checking, yes. And now we're going to need our x0. So what exactly is our x0 going to be? Well, as I said before, we need it to be an array, but since I put that jnp at least 1d in there, it doesn't have to be written as a jnp array. I can just put an array in. And so we know what these ones are, but I'm just going to go with 0. And then for this one, I'm going to guess a sign won't really matter, but this is always going to be positive. So maybe I should make this minus, make this like and jnp dot pi times that, because that's cool. Redefine u, that hasn't changed. So then maybe we'll just go like 4. And this one we're going to go with 2.222. So we're going to see, hopefully this works. Thinking. Return not a number. Is there something I did wrong with... okay, we can fix that pretty easily. We're going to go print x1 f1. Run this again. So it starts out with not a number. So it's saying our x1. Okay, so it's saying our original x1 is not a number. So is there something I did wrong with our initial values here? I mean, this has no domain issues. So it has to be something with our square root. But I'm confused as to why we're getting not a number for all of them. We should do 2. Maybe our numbers are getting too big. Let's try 0.4, 0.6, and 0.1. But these numbers, they're spiraling towards infinity very quickly, which is not good. So maybe I made this equation a little bit too crazy. I don't really know how, but I mean, this is definitely correct. This is good. I think it could be this one. Let's try doing it like this with division and division here. Fix it a little. There we go. Okay, so it was just too much multiplication all in one place. Those numbers were getting way too big, way too fast, so it was spiraling out of control. So, glad we fixed that. Run U. Then it takes a second, it chugs. And here we go. We have our 3 roots. So we have when x is equal to 3.84, when y is equal to 0.2, and when z is equal to 192, we get 0, 0, and 0. So an easy way to check that is to look at our first array. Well, our first array, one of these numbers, since we're using all 3 of them in here, has to match one of our numbers up here. So 0.8, 0.2, positive 0.2 matches, so that makes sense. Down here, this will be equal to 0 when this square root is equal to this. So either we get y is 0, but y isn't 0, but that's fine. Or this thing is equal to 0, so this in here is equal to 0, that'll give us a 0. So pi divided by whatever. But instead of checking that by, that's just like the mental way of checking it. Or this one right here, if this equals 10, this will be 0. So x divided by y divided by z divided by x divided by y divided by z squared minus 10. So how can we check to make sure that works? Well, we can just run func2 with, I'll just assign this to result, and here again. And because if we hover over result, or if we check our variable inspector, we can see that result is a tuple that has 2 items. Our first item is our x1s. So all we have to do is do res 0, run this. We get 0, we get 0. We get 0, we get 2. And we get almost 0. So that's strange. Maybe there's no way to make this one 0. That's possible. Because again, I came up with all 3 of these equations on the spot. So maybe having a square root and having the sign oscillate, that's not good. So we can change this to an exponential, maybe? There we go. That's all we needed. Having an oscillating function might have messed with it a little bit because it was trying to follow the gradient. It was sending it to a bunch of random places, and it couldn't actually solve anything. But an exponential, apparently, with this setup, actually works quite well. So we have, let's see what our res 0 actually is as well. So negative 0.8. So you'll notice that that one fits quite accurately because, again, one of these three has to be equal to, the inverse of this. So negative 0.8, we have 1.6 and 4.9. And so when we plug all those in, we get 3 sets of zeros. So all of that troubleshooting wasn't with our method. Our method was pretty much perfect, right to go, because adjusting it from a scalar to a matrix is very, very simple when you have the powerful tools like Jax, Jacobian, and Lin-Alg inverse at your hands. So thankfully that was pretty easy. And our functions that I made up on the spot were giving us trouble. But again, it's all on a hard day's work. We figured it out. We just messed around with our functions until we got something that would actually spit out a number, and I feel good because I got to make something up on the spot, and it made made it into a video, and it all still worked as expected. So I thank you for watching. I appreciate your very generous support. So thank you, and have a good evening.